To recap, in the last video, we did a gumball fit, which didn't fit the data so well. We calculated these simple plotting positions. I went over that in the lecture. It's just a very simple relationship here. It just says that, the biggest event has a probability of 1 over 32, which can, here you can see that's about a 13-year return period. The longer the data, the more these dots will go into bigger return periods. Whereas this one did seem to fit the data a little bit better, still not perfect. Okay, now what we're going to do just in the final video is look at how these will change with sea level rise. And we are going to go onto the UK Climate Projections webpage. I don't know why my link is not working there. Oh, yep, it's loading up now. Again, you will have to register for this. So this is where all kind of government standard UK climate projections are. They're mainly produced by the kind of Met Office. So first of all, if you haven't done so, you'll need to sign up and you need to register and log on here. It shouldn't hopefully take too long to do. If you again have any problems, the data is in there. And then what I tend to do is go up to products. Sorry, the web page is being a bit slow here. And what I do is do marine projections, which should narrow it down to 6 projections. Now you can use the data, or you can use the data and the plotting. So what I'm going to do here is use the projections from 2007 to 2021. There's longer projections that go all the way to 2300, the very long-term ones, but we'll submit a request. Sorry, I'm downloading a big file. It's taking a little bit of a while, so I think my computer's a bit slow. Okay, so we want marine projections for the UK. We want time varying. We can use that baseline. And these are different RCP scenarios. So a low emission carbon, a medium. So we're going to go for that. Let's go for the high one. And you can click at different points around the UK coast. You can see it's not very high resolution, but we're going to pick a point relatively close to Portsmouth, that one there. We want the data in CSV formats. I think we'll keep everything else the same and we'll click submit. Okay, so this will take a few seconds, maybe a little bit longer, but that should eventually download a file for us, which should come up with another page and then give us the option to download. Sorry about that. Okay, so here's our data. You can see these are what the projections like. We'll download that. It's produced a nice figure for us, but this is the CSV data that we really want there. Okay, so what we can do is go back to our downloads folder and just copy all of that over. There's the data licenses and things. It's best to, I often copy all of it over in case you need it later. Again, pop it into your data folder. Our data folder is getting quite big now, but we should have a, well, we've got the data there, which is a CSV, comma separated variable. No, that's not the one. Sorry, where is it? Did I copy it over? Oh, it's this plume one here. So this is the projections, but here we have our CSV file. And these are different percentiles, so it's kind of like 5%. So it's actually probabilistic. So rather than just giving us a single value, it gives us a range. So we've got the 50th is kind of the mean projection, but that's a comma separated variable. You can load that into MATLAB, but what I've suggested here is to call it mean sea level RCP 8.5 Portsmouth, because then if you load in another site, as we'll do later, you can see that works. Okay, so what we're going to do now is load in this data, and we're going to do this similar to what we did before. So I'm going to say the projection file is, and let's create a file name. We're going to go back 2 folders, into data, mean sea level, RCP 8.5, and then we're going to add to the SID, because we might want to, you want to do this for another site, and then .csv. So that should create the file name for us. Just check it does. Yep, that looks right. Or we can come back and check if it isn't right. And then here we can use the ops to detect import options on that file. Projective. Okay, and run that. I probably spelt it wrong. Detect. I'm quite dyslexic. So it says unable to find that file. So just check again. So it's data, MSL, RCP. I put a dot there. It's 8.5, but I don't have a dot in my file name. So again, don't panic. If something doesn't work, just logically follow the code and try and work out what is going on. Okay, now what we can do is use the preview, like we did before, to preview that file with those ops to see what it would load in. And actually it's already doing quite a good job here, so we probably don't need, we can probably go straight to the read table, and we'll read that table with the ops. We don't need to specify the file name. I think it's kind of got everything we need in there already. Okay, I'm going to switch this one off. Okay, so it's loaded it in as we want. And then what I'm going to do is say the years is t.column1. So that just gives us the years. Okay, and then the projection is going to be, so now we're going to download the projection, so PR, and this is T. And I want all of the rows, but I want just columns 2 to 10. So that's going to give me just the projections, so without the years. So these are just the projections that I want. Okay. And at the moment it's a table, but I'd prefer to be in an array format, so it's much easier to plot. So table to array PR. And now I should have an array called PR, which is just the projections. So these are probabilistic, projections here. So these are projections, so this will be the 5, 50th, 95th percent, and all of the other ones in between. Okay. Yeah. Okay, so now we can do a figure. And again, let's go up and nick some figure text just to kind of help us. And we can edit it. Okay, so now let's do a figure. And we are going to plot the, let's take this out. Title, I'm going to say, is sea level projections. The Y label is the sea level, or the level. In meters, the X is going to be years, or year. Okay, now I'm going to plot some different things, so I want the hold on. So first of all, I'm going to plot the year, ER, against the 5th percentile, which is PR, shift column 1, and let's plot that as blue. And then I'm going to plot the 50th percentile, which is column 5, and the 95th percentile column 9. It kind of gives you the range. So let's do that as red, green, so blue, green, black. Okay, so let's run that. And that should produce the figure for us. So there you can see that, there's a range, but the 50th percentile is sort of 0 to about half a meter. The upper percentile goes above 1 meter. Now I'm going to add a legend. So I want the 95th percentile, 50th percentile, and 95th. You could plot all of them, but I just want that kind of range here. And actually, I'm going to set an xlim as well. And here I'm going to do year 1 and year end. Again, I haven't hard coded it because, you know, if you use the 2101, but now it should go from the beginning 2007 to the end 2100. Okay, now what I want to do is extract the magnitude of the sea level. So the year of year R, which is, because this is a decimal year, so if you use the year function, it rounds it. So I want to find the row number when it's 2050. So there'll be lots of zeros, but eventually there'll be an I in there, a 1 in there, which tells me when it's 2050. And you can always check this if you want. So column 44, so sorry, row 44, you can go in here and check row 44 is 2050, which is right. Okay, now what I want is, I'm going to say my sea level rise, row 1, column 1, is equal to PRI1. So that's the 5th percentile. And then I'm going to put row 2 is going to be the 5th. This is just the sea level in 2050, and then column 3 is 9. I'll take the semicolon off the end so you can see it. So sea level rises 20 centimeters, 29 and 39 in 2050. Okay, now what I'm going to do is do another plot, and I'm going to plot my GeV distribution that I plotted up here. So I never changed that. That should actually be the GeV fit. The other one's the gumball. Let's just run that again. Okay, now I'm going to nick this code. Okay, now what I'm going to do is plot my GeV my gumball distribution down here. I'm actually going to make the line width a bit bigger. So it's 2. Okay, and then what I'm going to, let's put the hold on, make sure that's on there. Now what I'm going to do is add the first sea level projection. So sea level rise, 1, 1. So let's make this first one red, and then this blue to correspond with the blue. So that's the bottom one. We then had, so then I'm going to have the sea level 2, the sea level 3. We're going to have a green and a black here. Okay, and then what I'm going to do is I'm going to say I is find the return period that is equal to 1,000. In fact, let's just run this and then I will show you what that looks like in a minute. I'm going to take out my plotting positions, so we don't need that. Okay, so here you have your original curve, and then if sea level is to rise, it just pushes these curves up so that a 1 in 1,000 year today becomes a 1 in 11 years with the lower projection, a 1 in 5 or 6 years, and then a 1 in 2 years as sea levels rise. Okay, so what I'm going to do is I'm going to find that 1,000 line, and I'm going to use the same as what we did before, the y line function. So y line is the return level of GeV at I of the 1,000. I'm going to make that a dotted line with magenta, line width 2. So this should make it easier on the eye to follow. So yeah, a 1 in 1,000 years today becomes a 1 in 11 at the 5th percentile, a 1 in 6 or 7 at the middle, and then a 1 in 2 at the upper. So it shows you how, you know, as sea levels rise, events that occur once every 1,000 years are going to occur much more regularly, not because storms are getting stormier, but just because sea levels are rising. Okay, so what I'm going to do is I'm going to create just one final thing, my return period sea level rise, row 1, column 1. I want to quantify this exactly, so I'm actually going to use the interp1 function to kind of interpolate between. But the first thing that I put in is the return level GeV plus that sea level rise. So I'm going to put in, essentially that's putting in that blue line. And then we need the return period. So I plotted in the y is that sort of the level, then the return period. And what I don't want to know is what is that return level at the 1 in 1,000. Remember, I here is the 1 in 1,000. So basically this will tell me the bottom one, but it should see in a minute that there's, the 1 in a 1,000 year becomes a 16.9, so 17-year return period. So with even just 20 centimeters sea level rise, or whatever the sea level rise rate, 20 centimeters sea level rise, a 1 in 1,000 year event will become a 1 in 16 year event. So this is why you can see it's such a problem. So let's do that 2 more times, but this time we'll put in the higher sea levels, the 50% and the 95th percentile. So now so that should be row 3. You can switch it off just so it's the last one to the screen. So it becomes a 16-year return period, a 4-year return period, and a 1-year return. Now, obviously, if your data is slightly longer, if you're doing this in subsequent years to when I recorded this, these numbers might vary because you might have more data. Okay, well done. So you've done that for Portsmouth. So now you can have a go at doing it for Liverpool. So go back onto the BADC, download all the Liverpool data. You should be able to do that quite quickly. Go back here, go back onto this and download the nearest grid point to Liverpool. Make sure you save all the files correctly, and then you should be able to go here and just type in Liverpool. The only thing you might need to change is if Liverpool has different data lengths. Here you might want to put in or you might want to actually, rather than hard code it in here, have those as inputs as well. But everything else should run smoothly. So there's your final practical. And again, if you wanted to, like we did for tides, you could turn this into a function and run this across multiple sites around the UK.